Hello, and welcome to Section 3 of the Hidden Risks of Green Buildings course. The objective of this section is to identify steps that the designer can implement to avoid moisture problems when using new wall system products. The focus of Section 3 is to take an in-depth look at the intent of 14 materials and resources credits. Reuse of existing building components, the management of construction waste, materials reuse, amount of recycled content, the use of regional materials, the use of rapidly renewable materials, and the use of certified wood. New green materials can often meet requirements in several LEED credits. For example, organic-based insulation materials can satisfy LEED Material and Resource Credit 6 as a rapidly renewable material, Energy and Atmosphere Prerequisite 2, Credit 1 for Energy Performance, and Indoor Environmental Quality Credit 4.1 for low-emitting materials. Many new materials and concepts can also fall under the innovation and design process credit requirements for developing new solutions, employing new technologies, or realizing exemplary performance. We believe that it is reasonable to assume that if we are relatively unfamiliar with a new material's individual performance, then we probably know even less about the material's interaction with other adjacent components. Our ignorance about the performance of new materials should not be disregarded because the manufacturer of these materials assures us that the product is appropriate for LEED certified buildings. The recognition of additional risk in the use of innovative products, especially in the envelope and heating and ventilation air conditioning systems by the development team, should demand a higher degree of rigor in the evaluation of these products. As previously mentioned, the interaction between the heating, ventilation, air conditioning system and the envelope creates an unusually high risk area. The impact of this condition is that any deficiency in either system can cause dramatic building-wide moisture problems. It may be only a slight overstatement to suggest that there is no wall system that a creative architect can envision that a poor heating, ventilation, air conditioning system cannot destroy. Conversely, a well-performing heating, ventilation, air conditioning system can often compensate for a marginally designed or constructed building envelope to the point where many moisture problems may never be noticed. However, there is a point where even an exceptionally well-performing heating, ventilation, air conditioning system cannot compensate for a poorly designed wall system, especially a wall that allows rainwater intrusion or is excessively leaky to air movement. For example, this video clip reveals the amount of water absorbed by a wall insulation product. The experiment shown here demonstrates that many products intended for wall and roof assemblies could absorb much larger amounts of water in contrast to the data sheet, which indicates that it is a non-absorbing product. If there is water leakage through the water-resistive barrier, the use of this material in wall cavities could create massive mold problems, since the normal wet-dry cycling will not likely occur. A simplification of the above concept can be shown in this chart. The term good envelope design refers to the correct design and construction of the air barrier, vapor retarder, and thermal barrier. It does not refer to rainwater intrusion issues, since even minor rainwater entry past the water-resistive barrier can be problematic. Good heating, ventilation, air conditioning design refers to the proper building pressurization for the specific climate, proper dehumidification, and proper air distribution within a building. Although new wall system products are often intended to provide better thermal insulation, reduce air movement through the walls, or allow enhanced drying of the wall assembly via vapor diffusion, they can also perform in unanticipated ways. These new products can dramatically change the way moisture flows through the wall and roof systems and the potential for condensation within these cavities. For the use of these new products mandate that the designer implement several additional steps to avoid problems. Number 1, be sure to understand the performance characteristics of these new products. This may require a more rigorous evaluation of these materials than is required with traditional products. As with any product, but more so with new products, the performance answers may not be found in the product data sheets, but may require experiments and mock-ups to determine their performance. This type of evaluation may be beyond the scope and expertise of the design team, but it should nevertheless be implemented. Number 2, analyze the vapor retarder, air barrier, and bulk water retention properties to better understand where the material should be placed, if at all, within the wall system. Number 3, model the wall systems for performance during the early design stages to predict the potential for water vapor transmission through the wall assemblies and potential for condensation to occur. Minimally, this modeling should predict the dew point location and the vapor transmission profile during the most extreme season for the location. And number 4, perform a three-dimensional analysis of rainwater barrier geometry, especially at complex joints and changes in plane. All other standard good practices for wall system design should continue to be followed, whether new or traditional products are used, including implementing water-resistive barriers as the first line of defense, designing drainage planes to channel water down and out of the envelope, installing secondary barriers for redundancy, and designing proper flashing and sealant joints. This ends the Section 3 Learning Content material. Please proceed to the self-assessment for Section 3 or review the section video again.